So in this video lecture, we are discussing the relation between convergence almost everywhere and convergence in measure. And we have seen that if a sequence of Borel functions converges in measure, we can take a subsequence that converges almost everywhere. And we can take as an example, remember we had the dancing wave where for numbers between 0 and 1, this was my set omega, was the interval 0, 1, and we had some tiny wave like this that was moving as we increase the index until it would arrive here. Once it arrives here, it would come back here, but now with half of its size, and then do the same journey again. Of course, just now it would take twice as many indices to complete. Then again, would come back here and take a function with half of its size. This was what we called the dancing wave. And what would be a subsequence that we could take here? A subsequence could be take first the function constant equal 1, then take the function which is 1 only on this interval, but now skip the function that was taking value 1 here, jump and consider immediately the function that was taking value 1 here. And now again, skip this function that takes value 1 here, skip the function that takes value 1 here on the third quarter, skip the function that was taking value 1 on the last quarter, and jump immediately to this function that now takes value 1 here just between 0 and 1 over 8. And as you can guess already at this point, we're going to skip the function that takes value 1 on this second bit, third bit, fourth bit, fifth, sixth, seventh, and eighth bit. We skip all of them because what we are doing is we are building a subsequence. And then next function will be the one that takes value 1 here. And as you see, this sequence of functions, this one does converge almost everywhere. And this is what this proposition is saying, that if a function converges in measure, then a subsequence converges almost everywhere. And this example illustrates one possible subsequence. And now we're going to see a different implication. It's not almost everywhere implies convergence in measure. We don't have such a thing. We don't have that convergence almost everywhere implies convergence in measure in any sense. And the example we saw where this cannot possibly happen was what we call traveling wave. So this is a function that takes value 1 on some interval which is far away. And as we increase n, we are just moving this function and putting the function in a different place. And this keeps going. And there's no way to make from here conclude anything about convergence in measure, because then for every n we fix, and if we take here epsilon equal 1/2, the measure of this set here, the measure of this set will always be equal to 1. There's no way this is going to converge to 0. So in general, convergence almost everywhere will not imply convergence in measure. However, if we, instead of looking at the general measure, we look at finite measure, and for our purposes, finite, let's just assume probability measure to keep it simple. So if our measure is a probability measure, then yes, convergence almost surely will imply convergence in probability. So this proposition is saying that an example such as this one, the traveling wave, is only possible in a set that has infinite measure. And the proof of this proposition, well, is rather simple, given that we have already made an observation when we were studying Borel-Cantelli and infinitely often. It is the following. Assume xn converges almost surely to x, and this means, the remark that we did last week, that this means that the probability that xn and x is larger than epsilon infinitely often, that probability is 0, and that's 0 for every epsilon. But then we have also seen that if the probability of an infinitely often for every sequence an, if the probability of an infinitely often is 0, that implies that the probability of an tends to 0 as n tends to infinity. So we can, from this property, we can conclude that the probability that xn minus x is larger than epsilon, that probability will tend to 0 as n tends to infinity, again for every epsilon. So for each fixed epsilon, we are going from here to here. And since this is true for every epsilon, this is exactly the definition of xn converging in probability to x as required. And this will conclude this very brief video lecture.